Recording has started.
So for these two micrometers, they are metric. We can tell for a couple of things. The numbering on the main scale goes up by 5s. And on the thimble here, it goes up to 45, and then 50 is back to 0. Remember, a inch micrometer would only go up to 20, then 25 would be back to 0. So these are measuring millimeters. First one here, this is 5, 6, 6.5. Then what lines up here, this is between 33 and 34. Looks like it's closer to 33. That's 6.83 millimeters. Is that reading? The second one over here, this is 6, 7, 8, 9. And then it looks like it's between 29 and 30 on the thimble. Closer to 29. That's 9.29 millimeters. I'm going to have you read these two micrometers quick. We'll go over them in just a minute. So these are both inch micrometers. We can tell because it's labeled by 1s here on the main scale. And it goes up to 20, and then 25 is back to 0. The key here is the placement of the decimal point. These are all after the decimal point. This is 0.3, 25, 50, 75. So that's 0.375 on the main scale, on the barrel of that micrometer. Then on the thimble, it's between 11 and 12, looks like it's slightly closer to 11. That's 0.386 inches. That second one, 0.4, 25, 50, 75. And that's really close to the 12. 0.487 inches. I'm going to have you read these two calipers quick, and then we'll go over them in a minute. So these are millimeters. You can tell it's labeled on the dial there that it's 100th of a millimeter. But remember, this is centimeters, so that's actually have to be read as 10 millimeters. So that'll be 10, 15, 16, 17, 18, 19 millimeters. 0.48. That's 19.48 millimeters. Second one there, that's 30, 123.56 millimeters. We'll have you read these two. We'll go over them in just a minute. So these are inch calipers. And remember, the tricky part about the inch calipers is where the decimal point goes. The decimal point goes between the two numbers on the main scale. So this is 2.3. And then 53. So 2.353 inches. This is 1.5. And then 6.9 inches. Now, I had mentioned vernier micrometers to you. We didn't go over them at all the other day, but I just wanted to show you what they looked like. These are what the vernier micrometers look like. You can see here, they got these extra lines up here. Whichever one lines up with the thimble, that's that extra degree of precision. So this is 0.250. Then on the thimble, it's between 10 and 11, so we're going to read the 10. Then that's the 3 here that lines up, so that's, this goes on the end there. That's a 0.2603 inches is what that's reading. Okay, so enough of those. There is a quiz out there for you. On calipers and micrometers. It is due at noon tomorrow. Make sure you have that finished up and submitted. Okay, well, today we've talked a little bit about, precision and error and stuff like that in measurement. We want to talk a little bit more about that. We start out with something called an absolute error. Absolute error is just the difference between an actual value and the measured value. Remember, we've mentioned that anytime we measure something, we're limited by the degree of precision of the measuring device. So there's usually some small error built into every measurement because things don't come out exactly on the lines of the ruler or the measuring device. Typically, we're not quite as concerned about an absolute error as we are about relative error. The relative error is the absolute error divided by the actual value. So if we have something that's off by 1/8 of an inch, you might wonder, well, is that a big deal? Well, if it's off by 1/8 of an inch, as 1/8 of an inch absolute error, and it measures 40 inches, well, that 1/8 of an inch off, yeah, isn't such a big deal. It's literally 0.003125. Is the relative error. Now, some textbooks define them as something totally different. Some define them as just two different ways of writing the same thing. I personally see relative error and percent error as just two different ways of writing the same thing. Move that decimal point 2 spots to make that a percent. This is a 0.3125% error. So yeah, that's a pretty small error. But if we go back to that same 1/8 of an inch absolute error, and we are measuring something that's only 2 inches in size, well, that's a 0.0625 relative error, or 6.25% error. That's way too big. So the absolute error isn't nearly as important as that relative error. It depends on what the size is of what we're measuring. Now, this also helps us determine what measuring device to use. If we're measuring something that's only 2 inches long, we're not going to grab a ruler that only goes down to 1/8 of an inch. It's not precise enough to measure that very well. If we're measuring something that's 50 or 60 inches long, well, yeah, then we're going to take a tape measure that only goes down to the 1/8 of an inch or 1/16 of an inch. That'll be more than precise enough to measure that object. Well, another type of error in measurement looks like this. So this isn't really a mistake or an error of some sort, but it's an allowable error. It's called an allowance. So what this is saying is, in an ideal world, we want that to be 0.750 inches. That's called a desired value. But since we don't know we know it's not a perfect world, and we know that we can't always, cut things exactly the size we're shooting for, we are allowed to be off by as much as 0.005 of an inch. That's an allowance. So what this is saying, just like with our measurements, it's giving us an implied range. The 750 thousandths minus the 5 thousandths to the 750 thousandths plus the 5 thousandths. So there's our allowable range of sizes for that dimension based on that allowance that's given. So in your notes, I want you to find for me the allowable range for that measurement. So we go from 0.380 minus 3 thousandths, which is 0.377, 0.380 plus 3 thousandths, which is 0.383 inches. Now, you've heard me use the term allowance here. What about the term tolerance? Well, tolerance is actually the distance between the minimum and the maximum here. There's an allowance of plus or minus 3 thousandths of an inch. That creates a tolerance of 6 thousandths of an inch tolerance between the smallest and the largest dimension possible for that measurement. Now, we do sometimes list them like this. 1.2 inches minus 8 thousandths of an inch plus nothing. This is what's referred to as a unilateral allowance. Which means we can only be off in one direction. In a perfect world again, we want it to be that 1.2 inches. That's our desired value. But since we know the world isn't perfect, This is saying we can be a little bit smaller if we want to, but we cannot be larger. Now that, of course, gives us a range. .192 inches to 1.200 inches, which is the same range we would have got if we had just listed that as 1.196 plus or minus 0.04 of an inch. So why would we list it like this instead of just using our regular, what we call the bilateral tolerance or bilateral allowance, like we're normally used to seeing? Well, it comes down to what the desired purpose of the part is, what we really want the part to be. This is saying that if the world were perfect, we'd want it to be exactly 1.196. That's not true. We actually would like to have it exactly 1.200. So if I am looking to machine this, I'm setting my machine as close to 1.200 as I dare, knowing that if I have to, I'm going to be off by making it a little smaller rather than larger. Here, I'm just going to set the machine at 1.196 and let it vary in either direction, and I'm okay. If your machine is capable of machining within 0.02 of an inch, well, this one here, I'm going to, like I said, I'm going to set it up to shoot for 1.196. If it's given in this way, I'm going to set it up to shoot for 1.198 so that I'm shooting as close to that 1.200 as possible. Okay, so I wanted to make sure I give you some time today to get that quiz done. And my voice is not real strong yet anyway. I'm going to give you some homework on these errors and allowances. Page 198, 1 through 41, the odd. We'll give you some time to start on those. I will stay in here for a while if you'd like to get started on them and answer any questions. Otherwise,